You're welcome back. All right, so the third phenomenon we are going to consider under this topic is electric potential. Okay, now the same way electric field is measured at a point, or in an electric field intensity, please pardon me, is measured at a point in an electric field. Then we can also measure electric potential at a point. What is electric potential? Now, the symbol of electric potential is V. Electric potential is defined as the work done in moving a unit positive charge, okay, from infinity to that point, to a particular point, right? So let me define it again. Now, electric potential, which is measured at a point in an electric field, is the work done in moving a unit positive charge, work per, per charge, work per unit positive charge from infinity to a point in an electric field. Okay, so is measured in volts or abbreviated as V. Okay, so please take note of this. That is electric potential. So in terms of distance, okay, electric potential in terms of distance from a charge, that's exactly what we're going to express that formula in terms of distance. So you know very well that work is force times distance. Since we use R as the symbol for distance in Coulomb's law, so I'll just do FR. Okay, force, work is force times distance. Then divided by Q. We already know that force is, from Coulomb's law, is KQ square. Okay, then of course KQ square all over R square. Then don't forget, multiply by the distance R, still divided by charge Q. So I have to do some, breaking down. R divide itself 1, divide R square. I'm left with R. Okay, divide itself 1, divide Q divide itself 1, divide Q square half Q. So at the end of the day, I'm left with just K Q all over R. Now, let's actually establish a very important pattern that will help you remember the three formula that we've actually treated so far in these lectures. First, we started with electric force. If you can remember, vividly, the formula for electric force is KQ square all over R square. That is Q1, Q2. Okay. So let's say the two charges are the same, Q1, Q square. Okay. Then we'll now move on to electric field. A slight change actually took place. In this case now, I have KQ, not square again, then divided by R square. So they will now move straight to the electric potential, which, okay, let me use a different color. Okay, to electric potential. Here we have V now to be equal to KQ divided by R, as you can see. All right. So there is a kind of relationship that exists. The way the formula actually is actually progressing in this pattern. So that way you know that when you are talking about, when you are working on electric force, we have Q square over R square. Then in electric field, the Q is no longer square. It's reduced to Q rest. Okay, just Q, then R is square. Then of course, when you now get to electric potential, the Q is not squared, and of course the R is not squared. So that way, you can always remember the formula and not mix them up. That is really very important. Okay, now electric potential is a scalar quantity, so we don't consider direction. So rather, we can actually calculate electric potential due to system of charges. But before then, let's just look at a simple example. Okay, let's look at a simple example. So let's say you're being asked to calculate the electric potential at a point 20 cm from a charge of 5 microcoulombs. Okay, so of course this is very simple to solve. The electric potential is going to be equal to kq all over r. 9 times 10 raised to the power of 9 times 5 times 10 raised to the power of minus 6, then divided by 0.2. So I'm very sure that you can actually complete that. Now let's look at electric potential. Electric potential due to system of continuous electric charges, not just one. Okay, so let's say there's a point I want to measure an electric potential. Let's say this is a point. So here at this point, the electric potential at this point is also as a result of system of continuous charges Q1, Q2, Q3, okay, Q4, then Q5, 5 charges. So invariably, the work done is going to be first is going to be done for each of them, Q2, Q3, Q4, right? All of the charges. So invariably, the electric potential at this particular point, okay, the electric potential at this point is going to be the algebraic sum of the potential, okay, due to Q1, which I will call V1. Then potential due to Q2, that is V2, V3, V4, V5. So invariably, the total electric potential at this point, okay, is going to be the algebraic sum of the potential V1, V2, okay, V3, V4, then dot to any number. Okay, so please take note of that. So invariably now, you know how we write that. This is going to be KQ1 all over R1 plus KQ2 all over R2 plus KQ3. Okay, plus KQ3 all over R3 plus KQ4 all over R4. It continues, all right? So, of course, since K is a common factor, it is ideal to factorize this. So this is how you calculate the electric field as due to system of continuous charges. Okay, so of course you know what happens if this is 2 microcoulombs, this is 3 microcoulombs, and this is 4 microcoulombs. Or better still, let's say, let me just make it easier. Let's say all of them, okay, all of them are equal. Let's say Q1 is equal to Q2 is equal to Q3 is equal to Q4. Let me remove Q5. Okay, is equal to Q5, and all of them are 2 microcoulombs. Okay, so and let's say all their distance from that point are equal also. let's say it's 20 cm. So applying this formula, the total electric potential is going to be 9 times 10 raised to the power 9. The charges, okay, are the same. So I can also factorize it out. Okay, that is the charges are the same, which is 2 times 10 raised to the power of minus 6. Okay, I can factorize it out. The distance is also the same, which is 20 cm. That is 0.2 actually, 0.2. Then they are all the same. I just factorize it out. Then okay, so I have to open the bracket. So since both dq and r1 are all the same for all of them, I have taken them out. Then I'm left with 1 plus 1 plus 1 then plus 1. So at the end of the day now, in this case, all I'm doing is just to multiply 4 times 9 times 10 raised to the power 9 times 2 times 10 raised to the power minus 6 all over 2. So this is just a simple trick, just in case the charges and of course the distance are the same, so you don't need to go through all the process. Okay, so all you just need to do is to calculate for 1 then multiply by 4. So this may not be necessary, but if the distances are different and of course the charges are different, then definitely you will have to apply this formula right here. So I hope that is well understood. Okay, we are going to solve question on this, but let's proceed. This time around, let's look at what is known as electric potential difference. Okay, now in most cases it's also, we still use V to represent that. Okay, as the name implies, this is just a difference in electric potential between 2 points in an electric field. There's a charge that will measure the electric potential at a point, okay, point A. Then we also measure, okay, the potential of the same charge at point B. So invariably, the potential at point A, let it be VA. The potential at point B is VB. So between point A and point B, we'll have what is known as potential difference. So potential difference is simply the difference in potential between 2 points. So that is going to be VA minus VB. So if the distance for A is RA and the distance for B is RB, so invariably potential difference is going to be KQ divided by RA, then of course minus KQ divided by RB. So that way we can actually factorize KQ being a common factor. Okay, so this is going to be, I'm left with just 1 all over RA minus 1 all over RB. So this is the formula we use for electric potential difference. So to apply this formula, apply this formula is not difficult. Okay, so if you have two position, if you have 2 points of distance, RA equal to 20 cm and RB equal to 30 cm, okay, from a charge Q of 2 microcoulombs. The electric potential difference between these 2 points, of course, is going to be giving us from what we have here, K, which is 9 times 10 raised to the power 9 times Q, 2 times 10 raised to the power minus 6, then 1 all over 0.2 minus 1 all over 0.3. Okay, so 1 all over 0.2, let's do that. 1 divided by 0.2, that's a 5. Here I have 5 minus 1 divided by 0.3, 3.33, so approximately 3. Of course, this is going to be 18 times 10 raised to the power of 18 times 10 raised to the power of 10 raised to the power of 3. So this is 2 times 18, that's 36. 36 times 10 raised to the power of 3, also measured in volts, is the electric potential difference between those 2 points. I hope that is well understood. Okay. Now, let's summarize this. Let's look at the relationship that exists between, this time around, electric field, okay, and the electric potential. Electric field and electric potential. Electric potential between 2 points in terms of electric field is given as the electric field then multiplied by the distance between those 2 points. Don't forget this formula. So that is why we have, okay, the unit of electric field being equal to volt per meter actually came about. So electric field being equal to electric potential divided by distance is going to be given as volts per meter. So that is where the formula, that unit, derived unit, actually came about. Okay, so please take note of this. This is really very important. All right, so that is it for this video. We are going to look at more in the next video. So see you in the next video. Thank you very much.